Hi there, and welcome to Telefunkian, and welcome to part 5 of our series on the Roland TR-808 drum machine. In today's video, we're going to learn a little bit about the op-amps in the 808, what they are, what they do, and whether or not there might be an opportunity to improve the performance of the instrument by replacing these 40-year-old parts with some new and improved versions. I'd like to say a few words before we get started. In this video, we're about to remove 17 perfectly good functioning op-amps from an 808, replace them with socketed versions, and explore the potential for upgrading the instrument with new and improved parts. This isn't something you would normally ever need to do. I'm doing this with my own 808, one I've owned for more than 25 years and plan to keep for many years to come, purely for my own entertainment and hopefully yours as well. If you join me on this journey, hopefully you'll learn something. And if you ever find yourself needing to replace op-amps in your 808 or any other electronic musical instrument, you'll know where to start. So sit back, relax, and enjoy the video. The term op-amp stands for operational amplifier, and this name comes from the fact that in their earlier versions, these were used predominantly to perform mathematical functions or operations such as addition, subtraction, multiplication, integration, and the like in prototypical computer circuits that were being developed around the time of World War II. The symbol on your screen is a schematic representation of an operational amplifier, which has been reduced to its most simple form, consisting of a negative voltage supply, positive voltage supply, a so-called non-inverting input, an inverting input, and an output. From time to time, you'll see this symbol simplified even further, leaving off the voltage sources such that they're implied, meaning that they're actually connected but not shown in the schematic. When you see this symbol, you know it's an operational amplifier, and you know it behaves according to certain rules that govern the behavior of operational amplifiers in circuits, whether or not they're appearing in computing circuits or, in our case, in audio amplification circuits or instrumentation circuits. We use this same schematic symbol to refer to an op-amp regardless of the equivalent circuit contained within the individual amplifier. What's shown on the screen are two examples. One, the NJM 4558, which is the op-amp contained within the 808, and the NE 5532 equivalent circuit. The op-amps in the 808 are packaged in a standardized 8-pin package that contains two op-amp circuits in one chip. This is accomplished by sharing the pins that provide the power to the op-amps, giving us 2 pins for each input and 1 pin for each output of the individual op-amps. This standard packaging format has been shared amongst literally dozens of different op-amp circuits. Many of these are suitable for audio applications, and because they all share the same pinout, oftentimes share similar supply voltages and performance specifications, they can be swapped interchangeably between one circuit and the next. This process is often referred to as op-amp rolling, which is analogous to the tube rolling process that tube amp aficionados engage in from time to time, swapping out different tubes to see how that might affect the performance of their tube amplifiers. In today's video, we're actually going to be looking at the 4558 op-amp and seeing whether or not there's an opportunity to do some op-amp rolling and substitute the 4558 with one of these other 5 op-amps listed on the slide. Like anything else, the devil's in the details, and on any op-amp's datasheet, you're going to see a dizzying array of ratings, recommended operating conditions, and operating specifications. On this example, you can see towards the bottom of the slide that the recommended supply voltages for the 5532 op-amp ranges between 5 and 15 volts, positive and negative supply. These are some of the electrical characteristics of the same op-amp, and they include some specifications such as common mode rejection ratio, the small signal differential voltage amplification, maximum output swing bandwidth, unity gain bandwidth, and so on. So which of these do we really need to pay attention to if we're considering replacing one op-amp with another? Well, there have quite literally been a number of books written on this subject, but I'll try and distill this down to something bite-sized for the purposes of today's video. First of all, there's the supply voltage. What kind of supply do we need to provide the op-amp with? Audio op-amps tend to perform best with bipolar DC power supplies, both a positive and negative voltage. If you're considering swapping out an op-amp, you need to ensure that the circuit that it's going into is providing with the appropriate source supply voltages. In addition, different op-amps require different amounts of current. Since many devices utilize many op-amps in their circuitry, if you're swapping out op-amps, you need to ensure that you're not moving from a low current op-amp to a higher current op-amp and then potentially overwhelming the power supply that's supplying the power to the device. A relevant performance metric for op-amps for audio is the so-called gain bandwidth product, which is a measure of the bandwidth of the operational amplifier as you increase its gain. Gain with bandwidth product is typically measured in megahertz, and older operational amplifiers might have gain bandwidth products on the order of single-digit megahertz. If you're using these older operational amplifiers and expecting 1,000-fold gain, you may be approaching a bandwidth reduction that eats into your audio bandwidth. Another relevant performance specification is the slew rate, which is a measure of the op-amp's ability to change the voltage on the output in response to transient changes in voltage on the input. You can imagine that if we are putting a very slow sine wave, 20 hertz for example, through an op-amp, it doesn't need to change the voltage on the output very quickly. By way of analogy, the same signal at 20 kilohertz has to change voltages 1,000 times as rapidly, and if it were 20 gigahertz, you can see the implications. Accordingly, slew rate becomes an issue when we're looking at higher frequency or higher amplification applications. Input noise and harmonic distortion should be relatively self-explanatory, and lower is better. Common mode rejection ratio is a measure of the op-amp's ability to reject common mode noise coming through the input circuitry, and in this case, higher numbers are better. If we look at the schematic of the 808, we'll see 17 4558 op-amp chips distributed throughout. We'll see each of the op-amps in the schematic is numbered, but we've got examples where we have the same number twice, and this is just simply a representation of each individual op-amp within a 2 op-amp 8-pin DIN configuration being used in the circuit diagram. In some cases, we even have the same chip being used in different voices within the 808 itself. The 4558 circuit was actually developed by Raytheon in 1974, predating the development of the 808 by about 6 or 7 years. It's most commonly used by the company JRC, Japan Radio Corporation, which later became New Japan Company, NJM, in the 70s and 80s, and appears in all kinds of electronic consumer equipment, including a lot of musical instruments. The original JRC op-amps are sought after by guitar pedal enthusiasts who believe that they contain some sort of special mojo, and they're often used, somewhat ironically, in distortion pedals because they provide a certain quality of distortion, and it's believed that this brand is different somehow from some of the other brands, even though ultimately they all share exactly the same circuitry. It's important to remember that the main reason why the 4558 was used so frequently is because it was essentially the cheapest op-amp available at the time. Here we can see a number of the 4558's performance specifications, and as you can see, it's sort of in the middle of the pack in terms of both its requirements and its performance. It takes a voltage between 4 and 18 volts, and we know that the 808 has a 15-volt power supply. The 4558 uses 3.5 milliamps per amplifier, and you can see that one of the others, the 4562 that we're considering, uses 10 milliamps. So if we were replacing all 17 op-amps with the 4562 and we were trying to run our 808 off of a wall wart, which we're not, this could be a consideration. We can see the gain bandwidth product of the 4558 is superseded by the 4562 and some of the others by as much as 10-fold, while the slew rate is similarly relatively low when compared to some of the later op-amps. Although the total harmonic distortion and noise of the 4558 does not appear on its data sheet, the value shown here, 0.0004%, has been provided by an intrepid researcher who has published a study on his website, and you can see the URL towards the bottom of your screen. So clearly there are op-amps available that have performance specifications that beat the 4558, but how do we determine whether or not it makes any sense whatsoever to replace the 4558 with any of these other examples? Is there any way we can measure their performance in situ, as it were, actually in the 808? We're not about to desolder all of these operational amplifiers and put in new ones just to simply see if the instrument sounds any different. So we'd rather take a more scientific approach to this problem, and in this case I've taken a reductionist approach as a means of trying to determine whether or not there's any potential to tell the difference between the performance of the 4558 and any of these other candidates. Our test circuit is going to be the output portion of the 808. The portion that's illustrated or circled in red is actually a power on-off muting section that mutes the output, the audio output, when the instrument is shut off, and also protects the CPU from any spontaneous discharge so that the memory doesn't get erased when you're shutting off the 808. So we're going to ignore this section of the circuit for the time being. We'll focus on this section. This is the business end of the output, which consists of one 4558 circuit utilizing both op-amp circuits in the single chip, and it is in a configuration that we'll describe as an inverting configuration that we'll describe in a bit more detail in the next slide. We described the inputs to the op-amp as being inverting or non-inverting, and this is illustrated here where you can see the inverting op-amp configuration compared to the non-inverting op-amp configuration. You can think of the non-inverting op-amp configuration as providing you with a positive representation of the input signal. It may be amplified or it may be diminished by some factor, which we'll refer to as A for amplification. If you have a positive voltage on the non-inverting input of the op-amp, you'll have a positive voltage on the output. The inverting op-amp configuration, on the other hand, inverts the voltage such that if you have a positive voltage presented at the inverting input of the op-amp, you'll have a negative voltage on the output. That voltage may be larger in magnitude or smaller, depending again on A, the amplification factor that is applied in the circuit. For the purposes of using op-amps in audio applications, the use of the term inverting implies an inversion of phase, while non-inverting implies no phase shift associated with the use or the pass of a signal through that op-amp. You can see on your screen the equations that govern the behavior of inverting and non-inverting op-amps, and these are governed in turn by the value of two resistors in each circuit that uses an op-amp. One of these, RF, is a feedback resistor that joins the output of the op-amp to the input. Another, Rin, is a resistor between the input signal and the input of the op-amp. What you can see here is that the amplification of any op-amp is governed by these two external factors, these two resistors, independent of what op-amp chip is actually used in the circuit. It might be tempting to think that if you use a 4558 and replace it with an 072, you'll have a different level of amplification of your signal because it's a different chip. That's simply not the case. That's not generally how op-amps work. If we examine the output circuit of the TR-808, we can see that the 4558 op-amps are used in the inverting configuration, both of them in series. So the input coming into pin 2 of the op-amp on the left is coming in the inverting input, coming out on pin 1, going through a number of capacitors and resistors and going into the inverting input on the second part of the op-amp chip, comes out pin 7, and we can see from the circuit that we would expect the output from the left-hand side to be inverted in phase, and then the output from the op-amp on the right to be corrected and in phase with respect to the input signal coming from the left. If we're going to attempt to use this circuit as a circuit to examine the performance of different op amps, we need to understand how this circuit should be performing in its current state. We can see there are a number of resistors in configurations that resemble the model in the circuit diagram that I showed you previously, but there's also a number of capacitors that might affect the performance of the circuit as well. So let's discuss each of these in detail and try and predict how this circuit is going to perform in the 808 in its current state. First, let's examine the gain of the master output section of the 808. Earlier, I told you that the gain is determined by the value of the feedback resistor and the resistor at the input of an op amp. We'll consider first section 4B, the op amp on the right-hand side, and we'll consider it in a situation where VR1 is set so that the volume is all the way up, and essentially VR1 becomes equivalent to 0 ohms. The input resistance then would be 22K, and then we have a 33K resistor in parallel with a 330K resistor with a capacitor in series. So if we punch the numbers into the formula, we can see the resulting gain, and the gain of this stage of the op amp is 1.36. That is to say that any input at pin 6 on 4B will be amplified 1.36 fold and inverted at pin 7. But what about 4A? What's going on with the first stage of this op amp? Well, we can see a 33K feedback resistor, but what is the resistance on the input of this op amp? We can't see any resistor on this portion of the schematic, so let's peel back and see if we can determine an input point and an input resistor value so we can determine the gain of this stage of the op amp. Each individual voice on the TR-808 passes through a resistor which determines the extent of the gain applied to that individual voice. So in our case, we're going to choose to insert a signal on what's illustrated here as being lead 10, which would be the point at which the cymbal sound comes into the circuit that comprises the master output gain stage of the 808. The resistor here is 47K. We see that we have a 33K feedback resistor. We plug this into our equation. We get a gain for this stage of 0.702. We know that the gain of two sequential gain stages is determined by multiplying each individual gain, and the result of this is that we have a gain for the entire circuit of 0.95, or approximately 1. And this is important information because we need to know how much signal we should be inserting into this circuit and how much signal should we expect on the output of the circuit. So that helps us understand what sort of gain we should expect from this circuit. But what about all those capacitors that we saw? We know that op amps can be used to produce both high-pass and low-pass filtering circuits. And the way that they can be configured is illustrated on this slide here, showing the high-pass circuitry on the left-hand side and the low-pass circuitry on the right. By inserting a capacitor in series with the input resistor, we construct a high-pass filter which will remove low frequencies from the circuit. By inserting a capacitor in parallel with the feedback resistor, we construct a low-pass filter which will remove high-frequency information from the circuit. The equations that govern this type of behavior are shown on your screen, and they involve only the value of the resistor and capacitor, which can be used to determine the cutoff frequency of each high-pass and low-pass filter, respectively. If we examine the output circuit of the 808, we can see that each part of the 4558 op amp has essentially a high-pass and low-pass circuit associated with its behavior. And the formulas, again, governing this are shown on the lower part of your screen. If we insert the values for the individual components into these formulas, we can determine that the high-pass filters in the op amps have cutoff of 3.4 hertz and 14.5 hertz, respectively, on part A and part B, which is a cutoff frequency that would be inaudible to the human ear. Similarly, the low-pass filters have cutoffs of 21.9 kilohertz and 24.1 kilohertz, respectively, for part 4A and 4B. So now we've determined, at least mathematically, what kind of performance we might expect from this section of the 808 output circuitry. We need some way of attempting to measure its performance. Now, the equipment that's generally used to characterize behavior of op-amps when they roll off the assembly line is tens of thousands of dollars worth of spectrum analyzers and other equipment that I simply don't own. But what I do own is I own an analog discovery unit, which can utilize waveform software and conduct some basic measures of amplifier performance. So the first measurement we're going to undertake is a so-called Bode plot, which is named after a gentleman named Hendrik Wade Bode, who worked for Bell Labs on the development of some of the earliest operational amplifiers, some of those that were used during the war to guide anti-aircraft defense systems. And this Bode plot, named after Hendrik Wade Bode, is going to allow us to determine the low cutoff frequency and the high cutoff frequency, which we'll measure in hertz. We'll also be undertaking fast Fourier transform of the frequency spectrum of the op-amps as we pass a 1 kilohertz or a 10 kilohertz signal through the amp, and we'll determine the total harmonic distortion and the total harmonic distortion plus noise. We'll insert a signal here on the input, circled and labeled with a 10, the input where the symbol signal would be coming into the output amplifier, and we'll be measuring the output at pin 15 on the output board, which is where the master out comes out of the instrument immediately prior to the 10 microfarad bipolar capacitor, which is the second last thing the signal sees as it exits the instrument. Okay, now as we're about to take off these op-amps, I thought I would go through 3 different ways of doing this. One is to individually desolder each individual lug on the or pin on the op-amp. And then once all of the pins are freed, you can remove the op-amp. The other is to cut the pins off and then remove them individually from the board, and start with the more traditional approach of using a desoldering wick to remove the solder and then pulling out the op-amp. And we'll start with, let's see, who's going to be our victim today? IC 19. And so what we want to do is come real close to the pin with the desoldering wick. Ideally, we should see the solder flow into the wick and away from the pin, leaving a freed up pin. And there's a little bit of art to this and science. You can see that one was successful in that we have a freed pin, whereas this first pin was less so. We have some remaining solder. I'll move to a higher quality solder wick and see if that makes any difference. So this is a technique that you might be compelled to use if you felt that you were removing a chip that you were going to reuse somewhere, maybe replace it in, or take it out, test it, and ensure that it was working properly, and then put it back. That is not what we're doing in this case. We're replacing all of these chips, but I'm just going through this for illustration purposes. Was successful. Don't have to be too concerned with dwell time here, because the components that are surrounding this op amp are passive components such as resistors. We've taken all the electrolytic capacitors out of the board. If we were immediately adjacent to a transistor or another chip, we'd be a little bit more concerned about dwell time. But we're clearly not in this case. There we go. See, we're getting more flow with some of these pins than others. There we go. I want to see all that solder flowing up and into the braid. Okay, and you can grab the chip. There it is. See a little bit of solder still on a couple of pins. I can see solder on 2 pins. This one here. And this pin down here. And maybe that's done it. Yes. There we go. One op amp worth approximately 20 cents. That was tedious, and that's why we have other ways of doing this as well. So the next approach will be the cutting of the pins, followed by removal of the individual pins. And in order to do this, you need to have a good pair of cutters. Cut the individual pins from the top, like so. I don't recommend really reefing on these, because you have the potential to tear vias and the like, which again we don't want to be doing. And then oftentimes you can just get this from the top of the board, if we can find our tweezers. There they are. And there's our Of course, this is a terminal procedure. I don't think we're going to be able to salvage this chip. Don't know about you, but that's beyond my capabilities. Okay. So that was slightly less tedious. So this is the 808 after all of the op amps have been removed, and I'm now about to socket it. But first I'll describe what I've done in the meantime. I removed all of the op amps and cleaned the back of the board, removing all the flux and debris. I used this MG Chemicals flux remover for PC boards. I use this product from MG, or I use a more aggressive cleaner on some jobs, but I didn't want to go too aggressive with this. But as you can see, it's cleaned it up quite nicely. I will be cleaning it again after I repopulate the board, but I wanted to clean it up so we get good solder joints as we're soldering in the sockets and the capacitors. In addition, I cleaned the opposite side of the board, and you may recall it was filthy. There was a lot of dust, almost mud, really. And what I used to clean that was a combination of 70% isopropanol and 100% isopropanol, again from MG Chemicals. 70% is just the sort of stuff you'd find at your local pharmacy, but the other 30% is water. So I rinse it, I rinse the board off with absolute isopropanol, pure anhydrous, no water, and then I blow it dry. I'm also using a soft bristled paintbrush to break up any of the dirt that was there. Before the final clean, I squirted a little bit of deoxit into all of the switches, and I moved them back and forth several times to lubricate them and clean them a little bit. In addition, I removed the switch caps, and they're currently soaking in a product which is a peroxide cleaner, and hopefully that's going to brighten them up a little bit. I did not squirt any deoxit into these switches. They seem to be working reasonably well, and I don't want the lubricant and the deoxit to be attracting dust and debris, skin fragments and that sort of thing. But I did brush these out and blew them out several times, but I kept them dry throughout the entire process. I also removed the switch board and cleaned around the multiprocessor and the RAM chips, which are located beneath the board. Yeah, so what kind of sockets are we going to be using? We're using these sockets. These are what you call machine sockets, and they have the round receptacle for the pin, and they do a better job maintaining contact. For some reason, they're in this really tiny bag. I got these from Tata, probably about 20 cents each or so, which is roughly the same cost as replacement op amps. I've got two sets of op amps here. I've got the original, the 4558s, which do a reasonably good job, and I've also got some TLO 72s, which have the same pin out and have a slightly reduced power requirement and are lower noise op amp. And so we'll be trying these and see if we can discern any measurable difference between the two in the performance. So when replacing these, as you can see again, they have these nice round pins and round female receptacles for the actual chip, so they hold on to them really quite nicely. We'll be replacing, or rather putting them in place of the chips, and that will allow us to easily replace the actual IC. So if we just pick any one of these, and again you'll see that I've cleaned out all the remaining solder, so the the board is ready to be populated. Now, just a note, one has to be mindful of the orientation that these sockets are inserted, and that's really quite obvious based on the little graphic here where there's a cutout, and pin number 1 would be adjacent to the left-hand side of this cutout, and you want to make sure that you insert the socket so that it's in the same orientation, so that you don't inadvertently insert a chip in the wrong orientation. So begin soldering these, and I'm using this solder, which is a leaded solder. It's quite small diameter. It's 6040 0.6 millimeters with 2.2% flux, which is relatively little flux, so it requires very little cleanup. And what I generally do, although I'm not usually working on boards that are quite as large as this one, what I generally do is I flip the board over holding the socket and get a little bit of solder available. Move this so you can see it a bit better, hopefully. And clean my tip. Quite a bit of solder on there, and get a little bit of solder on one of the pins, and that will hold it in place. So then I can get a little bit more precise with my soldering. Hopefully I can do this without obscuring the camera too terribly much. You want to touch the pad. Make sure that you are heating the pad and the solder is melting into and through the pad. You may have vias, meaning penetrations in the board to the other side. This board is a double-sided board. You want to make sure the solder is flowing down and through that via and getting onto the pad on the other side of the board, if indeed there is one. Come to this last, or rather first pin, and remelt that solder and make sure it's a good connection. And then I like to inspect each individual socket as I go, and that way if I make any mistakes I know exactly where they are and I can fix them right away. And like this, one of these pins has too much solder. And one has not enough. There we go. And repeat. So let's repopulate the op-amp sockets, or rather populate them for their first time. What we're going to be doing is replacing the op-amp chips that we pulled out of the 808, which were these NJM 4558Ds, and we're replacing them with exactly the same type of op-amp. which you can see here mounted in this anti-static foam. And this is a mechanism whereby all of the pins are at the same potential and thereby protecting them against electrostatic discharge. So I believe there are 17 op amps that we need to replace here. So we've got 20 in this little package here. So let's see if my counting is right. Before we set about replacing the op amps, I wanted to say a couple words about making sure that all the pins are straight before we try to insert them. When you receive integrated circuits, brand new integrated circuits, they tend to have pins that are splayed out ever so slightly so that they're not going to fit into a socket. If you see the way that I've lined this chip up with this socket, the pins are actually too wide to fit into the socket. And if we tried to just ram this chip into the socket, we'd end up with bent pins and a bit of a disaster. And so prior to trying to mount the chip, we're going to just align the pins by using an empty socket, putting 4 of the pins in the socket, moving them slightly towards the center of the chip, taking the other 4 pins, moving them slightly towards the center of the chip. And they should now be in a position where we can get them all into the chip socket. And they are. So there we go. That's ready to insert into the socket. So a couple of comments about orientation. It's important that these chips go in the right way. And indeed, this little dot here corresponds to or denotes the location where pin number 1 is. These sockets have a little cutout, and that indentation again corresponds to the end of the socket where pin number 1 is. Pin number 1 would be this pin that I'm pointing to right here. I'm not sure if you can see that. I'll get something a little more pointed. That would be pin number 1, and so the dot goes in that orientation. So place the chip gently in the socket, and maybe I could have bent this one just a slight bit more. And once I'm sure that all the pins are going into their respective holes, press it down firmly, and there we go. That's not going to go anywhere. Next, you may or may not be able to see that I'm wearing an electrostatic bracelet. Not only am I working on the 808, which as a whole has a lot of static sensitive devices on it, but these chips in of themselves are also subject to destruction by electrostatic discharge. So you want to make sure that any static whatsoever that's built up in our body, or my body in this case, is dissipated to ground so that we don't destroy any of the circuitry. Static can even destroy transistors, believe it or not, and some of the transistors in the 808 are essentially unobtainable at this point in time, and we certainly do not want to be ruining any of those, because that would mean significant headaches for us. Whoops. If you see that bent pin, again, straighten that out before we try anything. Who would have thunk that something that seems so incredibly simple could actually take a little bit of care and attention? But it does. Just like anything else, it's worth paying attention and making sure you do as good a job as possible. Sadly, with the cameras in the way, I can't get my face in there well enough to see. My eyesight is not what it once was, so I'm fumbling a little bit here. Again, just bending the pins in ever so slightly so that the chip will fit in the socket. And I suspect that momentarily I'll be fast forwarding so you don't have to sit here and watch me do all of these. Where did I source these chips? Well, these chips are widely available, these op amps. They're pretty much cheap as borscht, as the expression goes. Hope that expression isn't offensive to anybody. They're about 20 cents or so, and I acquired them from a company called Teda, which is a company that I use to get parts for synthesizers and modules and various other things that I build from time to time. The shipping is, they ship from Asia. They're a little slower than, say, Mauser or Newark or one of these companies that tends to get you your stuff the very next day. But their prices are very good. And so for things like this, when I'm buying quite a few of any one thing at a time, it's worth going with Teda if I'm not in a hurry. And if the board wasn't so populated, I could actually do this using the socket that's actually mounted on the board, all this bending of pins. But given that there are all these capacitors and whatnot on the board, it's a little tricky. And this process is actually, it's worth it, because oftentimes the pins of the chip will be not only splayed out, but bent in other ways, and this process gives you an opportunity to address that before you try to socket the chip. And if you've done a great job, it should just pop in there, but I don't have a good batting average this evening so far. So that's 5. Okay. And make sure you double check the orientation of the chip once you've socketed it. It's really easy to take it out and flip it around if you put it in backwards. And if you do that before you power it up, you won't have destroyed anything. And I do have a pair of tweezers, which in theory make this easier. The pollen in the air this evening is intense, so my allergies are really acting up. And as I mentioned in another video, I'm not using any allergy medication this season, which makes it seem like I've got a constant post-nasal drip, but it's the price you pay. After doing this a couple times, you get a feel for how much you have to bend the pins in order to get them to sit in the socket. It's not very much, like 0.5 millimeter or so. But without doing this, you're pretty much guaranteed to end up with bent pins and all that jazz. Nobody wants that. Oh, see, that's what happens. Got a bent pin there, and well, I can straighten that. I'm sure it'll be fine. Another one. This chip might be cursed, or maybe it's the socket, I'm not sure. Okay. So, as we mentioned previously, part of the rationale for socketing these chips is not only to facilitate their replacement should any of them fail in the future, but these op amps are really pretty darn old in terms of their design. They're one of the more primitive 8-pin op amp chips that you can still find, and there are other chips that share the pinout and most of the functional features of these op amps that can be used in their place. And we're actually going to, once we are sure that the instrument is functioning as it should, we're going to characterize its performance slightly, and then we're going to actually swap out some of these older style op amps, older by design because these are brand new obviously, with some newer op amps, and see if we can measure any difference in the performance of the instrument, either in terms of its noise floor. Maybe there's a difference in sound. I doubt it, but we'll do our best to take some measurements and see if we can determine any difference, either subjectively or objectively. Well, that guy just does not want to go in, and that's because some of these pins are bent. It's pretty amazing that these actually cost less than they did when the instrument was brand new. I'm sure they do. And this should be the last one, bringing us to 17 op amps. That was a lot of desoldering, getting the old pins out. But the main reason I think that they didn't socket these to begin with is that the sockets aren't free, even though this socket here is again about 20 cents or so, and this is a higher quality socket than those that are used in most consumer grade equipment when they do decide to socket chips. That extra 20 cents a chip would have been deemed to have been too expensive back in the day when they actually made this instrument. It's quite rare that a socket would lose a chip, so the idea that they'd be less durable if they were socketed, I think is, I don't think that that's a reason why they wouldn't have socketed these to begin with. I think it's all about the price. Okay, we've got our cleaned covers for the switches, and these just pop right back on. They look a little paler, maybe a little cleaner. I'm not sure. I'll try to give you a better view of how these go on and off. So there are two tiny clips on each side of this square recess, and those will come down and capture this flexible black element which sits above the switch itself. The switch is really a four-part assembly. It's a switch which is a square component that sits in here, and then there's a black frame that sits around it, and this flexible bit is sitting above the switch, and it is the element that actuates the switch, and then there's the LED and then the switch cap. So these switch caps simply snap into place, like so, and they are approaching unobtainable, although you can salvage these caps from other instruments such as I believe the Jupiter 8. If you happen to have a Jupiter 8 sitting around in your basement that you're using for parts, I think you can salvage a few 808 switches from it. There was an organization that sold replacement switch assemblies for a while, but I believe they are no longer on the market. And other than cleaning these switches, I haven't done anything else to them. I've cleaned the switch caps, and then I've dusted out the actual switch assembly. I have not lubricated it, deoxed it, nothing of that nature. I don't want anything in there that might be attracting dirt. And I need one last switch. And again, to remove these, simply place a screwdriver underneath the front end of the switch cap and give it a slight twist until it comes off. Unless you're really rough with it, you shouldn't be able to damage it. So, if everything goes according to plan, we should have a functional 808 here. And now to reassemble the instrument. First thing we'll do is get this board mounted on the top panel. Here we're about to change the op amp in the output section of the 808, and I'll just show you exactly how I'm doing that. First, making sure that the 808 is turned off, flipping up the circuit board like so, and then very gently prying the chip up, pulling it out, then grabbing a replacement chip. In this case, we're putting in a TLO-72. Making sure the orientation of the chip is correct. That is with the number 1 pin towards the upper side of the board and the left. And of course, making sure all of the pins are properly oriented before pressing down firmly into the socket. And once the chip is in the socket, it's in there pretty securely. Gently placing the board back into the chassis and turning the board back on, turning the instrument back on prior to undertaking the assessments. So we simply run a Bode plot using a 3-volt amplitude input signal, which gives us an output of the phase response and frequency response between 20 hertz and 200,000 hertz. So we can see that the peak at 1 kilohertz had an output of negative 0.356 dB. So we want to look at the bottom cutoff, which would be negative 3.56 dB, and that is right around there at 54.2 hertz. And the top end of the cutoff is at negative 3.35 dB. And that is right there at 13.5 kilohertz. We'll just save this. We'll export it. This. So that's TLO, actually it's not an 85, it's a TLO 72 Bode plot at 3 volts. And come back to the wave generator. Set it up for 1 kilohertz at 5 volts. Start that running. Go over to the scope. Make sure the signal is undistorted. And stop the scope. And head over to the spectrum analyzer. And make sure the spectrum analyzer is set up for 1 kilohertz measurement. And set that to run. Now the spectrum analyzer will take 500 sample count and average those. So this will take a minute or so. So I may speed the video up. Great. Now the FFT is finished. You can see the difference between the input in yellow or orange and the output in blue, which are almost superimposable as the gain is approximately equal to 1. You can see the total harmonic distortion on the output is 0.0189%. However, we need to subtract the input distortion, which is 0.0149%. Similarly, the input and output noise values are shown there. I'll just write those down. And then we'll make some changes to the wave generator. We'll turn the wave generator to 10 kilohertz. Start that. Make sure that the signal is not distorted. And initiate the
Shown on your screen is a Bode plot of the 808 output circuit after a filter sweep from 20 Hz to 200 kHz with an NJM 4558 op amp installed in the relevant position in the circuit. This is with a 3 volt peak-to-peak input. You can see that the low frequency cutoff is 54 Hz and the high frequency cutoff in this case is 13.6 kilohertz. The results from all 6 op amps are summarized on your screen. We can see that the low cutoff is roughly around 54 Hz in each case. the high frequency cutoff varies slightly, with the LM358 providing the lowest high frequency cutoff of around 12.5 kilohertz. The TLO72 slightly greater than that and roughly equivalent to the NJM 4558, and the rest of the op amps essentially all at 14 kilohertz. So if we summarize these results, we can say that generally we've observed that most of these op amps are performing equally well, with some slight variation, with the more primitive op amps having slightly reduced bandwidth. But we expected the bandwidth of the op amps really to be dominated by the filter setups as a result of the capacitors in the circuit. So perhaps this isn't terribly surprising. There were very small differences in high frequency cutoff, and both the high frequency response and low frequency response were quite reduced relative to what we had predicted based on simply the value of the capacitors and the resistors in the circuit. So I find that result to be quite interesting, and I'd be interested in your thoughts on the matter. Why is it that when we did the math, we calculated a greater bandwidth than that we've observed here experimentally? Put your ideas in the comments below. The summary here, however, is that in terms of the frequency response, there's no obvious benefit from switching any of these op amps versus the 4558. But what about distortion? Are any of these op amps cleaner than the others? Well, if we look at the 4558 at 1 kilohertz, we can see that there are a number of harmonics that show up in the frequency spectrum. However, the second harmonic is reduced relative to the primary signal by almost 80 dB, which is really pretty darn clean for an electronic music instrument, and certainly below any level that you would likely hear. The measurements here might have been subject to limitations in the instrumentation. We had to remove the input distortion from the output measurements in order to measure any relevant differences. What we were able to see is that in the case of the LM358, that the harmonic distortion was considerably greater than any of the other op amps. And so this is obviously not an op amp that we would want to select if indeed we were going for a high fidelity version of R808 or any other electronic musical instrument. When we examined distortion at 10 kilohertz, we saw a number of artifacts both in the input signal around, say, 50 kilohertz, for example, and the output from the 4558 around, say, 54 kilohertz, for example, that were difficult to explain. They were not harmonic. They were likely introduced through either the instrumentation being used to measure, maybe the power supply, for example, for the analog discovery unit was introducing this noise into the system. Difficult to say. I haven't given it a tremendous amount of thought. But again, I'd be interested in your thoughts, and leave your comments below. Regardless, this distortion is rather low level, and it's certainly at frequencies that are beyond the range of human hearing, but I found it an interesting observation nonetheless. Again, when we went to more primitive op amp like the LM358, at 10 kilohertz, we saw an increase in harmonic distortion as well as these artifacts, which were present in every op amp that I examined. So again, I associate these particular artifacts with the instrumentation setup rather than the op amp itself. So the fast Fourier transform distortion measurements and noise measurements are shown on your screen. And again, we have a number of findings that we can summarize. And other than the LM358, both the distortion and the noise were at levels that were beyond human perception, at least in my view. We're looking at distortion levels below or around 0.01%, and that's including noise at 1 kilohertz. And in some cases at 10 kilohertz, the levels were so low that they actually were negative, which of course is meaningless and suggests that they're beyond our ability to measure them. And so we have limits in our instrumentation setup. So again, the summary here in terms of the distortion measurements would suggest that there's really, again, not an obvious benefit in the context of an electronic musical instrument like an 808 to switch op amps to a higher performing op amp. It's not going to result in a change in the quality of the sound that you will actually be able to hear. Now, again, there are some limitations to the approach that we've taken here. We've looked at one op amp, which is being used in one part of the circuit. However, even though there might be 17 of these chips in an 808, in any given signal, there may only be 3 or 4 chips maximally in the signal chain leading to one particular voice. So again, I'm not sure that changing all the op amps to a higher performing op amp in your 808 is really going to give you any benefit that you can discern with a human ear. And again, to reiterate, these are the findings summarized. If we were to ask the rhetorical question, should you go op amp rolling in your 808? Well, the original op amps, the NJM 4558, either the NJM version, the TI version, whichever manufacturer is making the chip, I would suggest that they're perfectly acceptable for use in an analog drum machine like the 808 in spite of their 45-year-old design. So really, that's quite impressive, if you ask me, that these things were designed as long ago as they were, and they sound as great as they do. If you needed to replace an op amp in your 808 because things happen and op amps do go bad, I've had op amps go bad in 808s before, there are several suitable alternatives, such as the LM4562 or the NE5532. But in my humble opinion, efforts to improve the sound of your 808 might be better spent identifying other sources of noise or extending the frequency response at the other end. Other sources of noise that might lead to hiss, hum, that kind of thing. Making sure your power supply is in good shape. And in terms of extending the frequency response at the other end, make sure, for example, that all your electrolytic caps are behaving properly. Keep in mind there's a non-polar or a bipolar electrolytic on the main output that all of the instruments go through, and that cap is one of the first candidates to be looking at to make sure that it's working properly. And in our case here, we've replaced it with a Nijicon Muse. So I hope this has been interesting and entertaining. I'm not necessarily suggesting you shouldn't mess around with your 808. I've enjoyed this process myself. I've learned a little bit in the process, and I hope you've learned something too. So if you've got one of these instruments, by all means, dig in. But as one of my viewers recommended, just don't break anything. These things are worth a lot of money. They're not making them anymore. They're making lots of copies, but they're just not quite the same. So have fun, enjoy, and thanks for watching.